Here we go.
Are we ready?
I think so.
All right, audio is working. All right, welcome all to Hyperon workshop. Hyperon. This is a compressed compared to previous AGI conferences, so we'll all talk really fast. Because I decided to try morning of Hyperon, afternoon of predictive coding this year because I was interested to sort of open up the predictive coding topic, and we've been doing dedicated Hyperon workshops for folks closely involved with that project, which is like 3 or 4 days for each workshop twice a year. And we find a 3 or 4 day workshop on Hyperon stuff twice a year is not nearly enough. Like in those 3 or 4 days, you're barely getting through the top level of all the different stuff that's going on in the project. So the 3-day Hyperon event sort of feels like the executive summary of things. So then this is like the little tiny mini abstract or something. And then what I will now give is the abstract of the abstract, I guess. Before that, the main thing starts. What we're talking about here is Hyperon, which has grown out of the OpenCog AGI platform architecture and project, which itself grew out of Novometic Cognition Engine, which itself grew out of the WebMind Cognition Engine from the late 90s. So this is the latest in a series of architectures attempting to create AGI by combining different learning and reasoning paradigms within a shared cognitive architecture that then learns from experience, both supervised and unsupervised, and self-modifies to improve itself as it grows. So the philosophy underlying Hyperon and its predecessors was fairly simple at core. I mean, you're looking at a mind as a complex, self-organizing system, which is recognizing patterns in itself, recognizing patterns in the world, among other kinds of patterns, recognizing patterns in which of its actions lead to this result. And you're looking at a mind as an open-ended intelligent system, which is trying to maintain its boundaries and its integrity while also self-transforming and improving itself to bring itself to new states that it couldn't have previously even understood. And you're trying to do this via whatever means will work, basically. So the high-level cognitive architectures I've been using in this series of systems have been roughly modeled on the high-level cognitive architecture of the human mind, meaning you have episodic memory, you have declarative memory, you have procedural memory, you have working memory. You're perceiving things, you're issuing actions, and you're trying to, among other things, choose procedures that will help you achieve certain goals in certain contexts. There's also a certain amount of sort of ambient self-organizing activity going on that isn't oriented toward explicit goal achievement. But while high-level cognitive architecture that we're looking at in Hyperon is roughly inspired by the human mind, we're not trying to copy exactly what the human brain does, partly because we don't know a lot of what the human brain does, partly because the hardware infrastructure that we have on hand is very different than the wetware infrastructure in the human brain. So we've taken a cognitive architecture roughly inspired by human cognition, and then the different core aspects of learning, reasoning, and memory are filled in with a diversity of different data structures and algorithms coming from cognitive psychology, from computer science, from the traditional AI field, from mathematics. And then we're integrating these things together within a sort of meta representational fabric and operational system that lets different sorts of algorithms and data structures all cooperate, right? So what this boils down to in practice, we have the Hyperon software framework, which I'll describe loosely in a moment, and we'll hear more about shortly. Then we have, on top of that, one could build many things. There's a specific cognitive architecture called Primus, which in honor of which we have Optimus Prime here, right, in front of the room, right? And then who's, I mean, highly ethical AGI system, Optimus Prime. I mean, he's kind of cloying, to be honest. I'm hoping we can get a more winning personality somehow. But I mean, as a start, he wouldn't be terrible. At least he's funky, right? I mean, Primus is cooler than Optimus. Primus can turn into a planet. Optimus just turns into a truck, right? But I mean, we could expand in multiple directions. You know? The Primus cognitive architecture is a cognitive architecture aiming human level AGI built on top of the Hyperon infrastructure. And we'll hear a bit about both during these next couple hours. So the Hyperon infrastructure is more new than the Primus architecture because my cognitive architecture ideas have evolved over the years, whereas my thinking about how to build an efficient infrastructure to realize these has changed much more greatly, just as the hardware has evolved and associated tooling has evolved. So regarding the Hyperon software layer, before we get to the cognitive architecture layer, Hyperon software layer, the key element is what's known as the atom space, which is a weighted label type metagraph. So it's nodes and links. The links can point to multiple nodes, the links can point to subgraphs. Nodes and links can be labeled with various weights and types. Types themselves are chunks of the same metagraph. And this is intended not to be a commitment to a particular low-level knowledge representation, but rather as a rich sort of meta-representational framework that can be used to implement a neural net, could be used to implement different logic systems, could be used to implement different sorts of programming languages. So you have a flexible representation fabric. And then we have a programming language called MeTTA, M-E-T-T-A. And we announced a language called MeTTA a few years ago. Then like 2 months later, Facebook changed their company name to MeTTA. So then we created a crypto project called the Artificial Superintelligence Alliance. And now like a year later, Facebook has launched a superintelligence lab, right? So I'm starting to think of how I can game this trend somehow. I'll pick a really stupid name and see if they'll go for it. Right? So yeah, when you see the artificial shithead intelligence, it's just to see if Mark Zuckerberg copies me somehow. But yeah, the meta language, METTA, not meta, although it is meta, but that's a different, but not that meta. The meta programming language originated basically with the idea that we want a language which consists of metagraph rewrite rules, which are then embedded in the metagraph. So chunks of the M-space metagraph can be sort of activated and then used to rewrite chunks of metagraph into other chunks of metagraph. And at that level of abstraction, it could be a bit like replicode, which we talked about in the 2012 AGI summer school in this building, Kristen Thorson and co, which was in the era cognitive architecture. I mean, the replicode is also a language of rewrite rules and rewrite rules to get new rewrite rules. Now, digging into the details, we've done a bunch of, I think, more sophisticated functional and logic programming stuff in the meta language. And in terms of the implementation of the meta language, a lot of work has gone on in the last few years aimed at getting that to really work nicely. And you could already see some of the issues confronted there looking at replicode. Like in 2012, there was a really fast replicode compiler written in C or C plus, C with little C++, and it was very fast. Only one person understood it. It was super hard to modify or work with in many ways that I wanted to. Then I think a guy named Martin Sandsmart tried to rewrite it to be more elegant, but then that wasn't as fast. So we already had there some of the dilemmas we've been wrestling with meta, which is we want a really, really performant underpinning, but we also want an underpinning which we can evolve over time as AI advances, and which ultimately the AI itself will be able to evolve over time. And so we've spent a lot of time on that in the last couple of years and made a lot of progress. We don't yet have a really fast, fully general meta compiler. We seem to be probably within like a month or 6 weeks or something of having that, which is quite interesting. And I think due to the work of Greg Meredith and Adam Vandervorst, who's here in the room, and Luke Peterson and a number of others, we have something called the meta optimal reduction kernel, which is a really fast atom space. So it uses some funky zipper machines built over prefix trees as well in Rust to make it really fast for pattern matching and many sorts of unification queries on an atom space. So that's sort of the heavy lifting. And so we're now mostly through the job of making a fast meta interpreter that backends mostly on this more fast atom space. And part of what we'll talk about today, though, is some of the core cognitive algorithms we're interested in, how to implement them in a way that's super, super fast and customized for more. So we're now sort of hitting a next level of implementation decisions, like assuming we, in a month or two, actually get the fast meta compiler, and it seems it's very close, and we'll talk about that later. There's a couple options. One is just implement stuff in meta and let it run on that fast meta compiler. Another is go the next step and take your algorithm and heavily customize it to run really, really efficiently in like more level assembly language, so to speak, right? And on the other hand, these are like high-class questions to be worrying about, right? Because a few years ago, we were worrying about like, do we even have any idea how to implement any of this shit in a scalable way? Or will it just be, 10,000 times slower than neural nets still after the singularity, right? So we're definitely on to the next level of challenging choices about scalable implementation, which is really quite interesting. The final element to mention implementation layer wise is the distributed aspect. So there's something called the distributed atom space being built by Andre Sena's team out of Brazil, which is a scheme for letting large atom spaces be split up and distributed across a bunch of different machines. And that's making progress. There's a bunch of funky stuff in there that's being prototyped now. For example, if you need to match a pattern against a large atom space, you can do some sort of reasoning in the distributed atom space's query layer to split up into sub queries that will be executed against parts of the large atom space that's stored in different machines. Then there's a decentralized infrastructure, which is part of Greg Meredith's Firefly / Metacycle / ASI chain work, where you can take different atom spaces living in different processes or on different machines, and you can compile the meta language into Golang, which is a sort of blockchain smart contract language. Then you can use those Golang smart contracts resulting from meta compilation to coordinate together different atom spaces on different machines, right? So that meta to row compiler is there now and is being ongoingly improved. But this means you can run atom spaces distributed and decentralized, right out of the box, which again has been a lot of infrastructure work because we wanted, like, assuming we do make a breakthrough to AGI with all this, right? We wanted it to be immediately possible to run this with a decentralized network, as well as on a big centralized server farm, if that's what you want to do. So all that is the infrastructure. You can use that infrastructure actually for a lot of different things. I mean, you can implement NARS on that. And in fact, it's been done. We do have an implementation of NARS on that, thanks to Patrick and Peter, who just walked in. You can implement neural nets on that. And we've been exploring some ways in which it may be very valuable to do that. Like if you take a wavelet CNN or a waveformer, a neural net with a sort of hierarchical structure built into it, that maps very neatly into the more prefix-free infrastructure. Then you have, so for certain types of neural net architecture, I mean, the more infrastructure we have underlying the atom space now might be the most efficient way to do it, as well as a really transparent and easily manipulable way to do it. On the other hand, I don't personally think either of those is the best way to AGI, although they might be cool ways to AGI. As I said in my introductory remarks earlier, there may be a lot of different ways to get to AGI, right? But the route to AGI I'm most optimistic about is the Primus architecture, which most folks in this room have heard me talk about before, so I won't say a huge amount about it, but we'll highlight a bit the new elements there, maybe before going on to whatever comes next. So that in terms of the atom space, Primus uses the atom space to store a variety of different types of memory, and you can look at it by enumerating the key types of memory in the human mind, like declarative memory, procedural memory, episodic memory, sensory memory, sort of action or motoric memory, memory regarding goals. We then associate appropriate learning and reasoning mechanisms with each type of memory. So we do explicit logic with declarative knowledge. We do evolutionary program learning or different sorts of reinforcement learning with procedural knowledge. For attentional knowledge, we do different sorts of activation spreading type things to spread attention through a network. For declarative knowledge, we also have concept formation algorithms like concept blending or fuzzy formal concept analysis. So you're taking a variety of different learning and reasoning algorithms associated with a number of different types of memory, and you're getting them all to work in this same big M space metagraph. And the reason to do it in this tightly integrated way, rather than putting your different cognitive algorithms in different sort of black boxes with cables between them, the reason to implement the different types of memory associated with the human mind and learning and reasoning mechanisms associated with each of those types of memory, the reason to implement all these in the same big M space metagraph is because of what I call cognitive synergy, which crudely means if you have different AI processes trying to help the same AI system, but by doing different kinds of thinking or different types of knowledge, you want all these different AI processes to be able to share intermediate state. So if one of them gets stuck, the others can help it out. So if one of them needs acceleration, the others can help it accelerate. I mean, sort of on the principle that working closely together and sharing as you go along is more efficient than having just different AI agents operating in black boxes and sharing only end results. So if you want to get that cognitive synergy where different AI methods doing different sorts of things with the common goal of making the same organism, survive and flourish and individuate, self-transform. I mean, then you need a common meta-representational fabric for all of these different AI methods, and that's what Hyperon infrastructure and Atom-Space provides. And within this overall framework, it then devolves into a whole bunch of detail, right? So we have the PLN logic framework running within Atom-Space. We have Moses as an evolutionary program learning framework. We have ECAN as an attention allocation framework, and a whole bunch of other things. In terms of high-level control, I'll talk about that a little later when we get to the meta motivation system. But in terms of high-level control, you can sort of divide it into ambient self-organization activity versus goal-directed activity. And I think they're both important. I mean, you could implement just a big self-organizing network and try to coax general intelligence to crystallize out of it. I think that could work and is really cool. I don't think it will be the most efficient way to get there. I think having explicit goals on different timescales, having the system trying to use is assemblage of AI methods to achieve these goals, given the observed context, is just the more efficient way to get shit done, which is why the human brain has that aspect to it also. It just shouldn't be dominant. Like you don't want to be 100% like reinforcement learning or goal achieving machine. You want to be that to a certain extent, and then let the spontaneous, unsupervised self-organizing stuff roll in your unconscious to a certain extent also, right? And we have both of these aspects, and they can both leverage the same cognitive mechanisms to a significant degree. So where we're at now with the project, to wrap up finally, where we're at now, we have a lot of the scalable infrastructure working. We have Morph working, we have meta language interpreter, where we should be launching within the next couple months, scalable general meta interpreter, as well as the first version of this decentralized infrastructure, the ASI chain. We have the distributed atom space in a sort of alpha version where you can run it and play with it. The interfacing is being worked on. So the infrastructure is coming together quite nicely. And we're now at the point where we're taking the core cognitive algorithms, PLN, Moses, concept formation, ECAN, and we have simple meta implementations of all of these already existing, but running at a very small scale because the meta interpreter so far has only let you do things in a small scale. So during the next 6 months or so, we'll be experimenting with these core cognitive algorithms at a large scale for the first time. And that's quite exciting, right? And it's hard to say exactly how fast things proceed there. I mean, you could have some things where the first time you run them on a really large atom space and a lot of data, they start to do something awesome, which you didn't imagine they would do. You may have other cases where the first time you run something on a lot of data, you find the whole algorithm was a piece of shit, and yet you have to go back to foundations and rebuild a better approach as fast as you can, right? You may find some things when you let them interoperate together at scale for the first time, they synergize and help each other and accelerate each other. You may find other cases where one algorithm didn't, in practice, help the other algorithm or understand its internal representations as much as you thought it would. So there's certain to be a lot of learning to happen, but it's a kind of learning we weren't able to do because we didn't have a scalable underpinning. And it's really similar in my mind to what's happened with deep neural nets in the last decade or so, right? Because I mean the path from LSTM to transformers, or from early CNNs to modern computer vision systems, is not that big in architecture design space, really. I mean, they're not to downplay the advance of people who invented transformers. I mean, it's all cool, but it's not, I mean, it's not that huge a leap from LSTM, as Jürgen Schmidt has told us many times. And I mean, that as Jan LeCun has told us, the step from early CNNs to modern computer vision systems is not that big either, right? I mean, to make these modest advances in design space, you just need to be able to run a lot of scalable experiments, look at what worked and what didn't, and then go back and think and adjust, right? So I think we're about to start that phase for the Hyperon system where we can run scalable experiments and then figure out what variations of the architectures and algorithms and representations that seem to make sense, figure out what variations of those actually work really well, which is a sort of one you can only do in an iteration between scalable implementation and theory, right? So that's a quite exciting time to be at. Of course, it's an unpredictable process. My gut sense is it's not going to take 10 years. I mean, for what it's worth, I mean, my gut sense is we may be 1, 2, 3 years from huge breakthrough toward human level AGI. And when I first started work, I've told this story before, but it keeps getting more and more poignant, right? When I first started working with Nil on AGI-oriented reasoning, it was right around when we launched the first version of OpenCloud, 2008, I guess. And Nil said, well, I think it's going to take us about 20 years to get to an AGI. And I'm like, I hope it doesn't take that long, but if it does, I'll probably still be alive then. So I mean, it's not that bad for it. So it's been a fun 17 years since that time. Not, and I think now he was about right. I mean, that seems like a reasonable time frame. And, so I think Neil should be the new Ray Kurzweil. We should not nominate him to predict all our timelines. So, until we have his digital twin, which will be even better. Yeah. So yeah. All that said, I know we're running super late, but let us move on to whatever is next in the agenda.
Wonderful. Alexa, your end is on first.
Yes, Alexei.
Okay.
So we have Alexei Potapov, who, thanks to the wonders of our human-run geopolitical system, did not get a visa to come to Reykjavik, coming straight out of St. Petersburg.
Alexei, can you speak?
Yeah, I
All
Yeah.
right.
Yeah, I've been following Alexei's work since around the time I met Neil, actually, almost 2 decades. And we've been working together, talking about working together, doing a little bit of work together for maybe a decade almost. But then I remember he visited our AGI lab in Hong Kong. It might have been 2015 or something. And then since 2018, been working more intensively together on OpenCog and Hyperon stuff. So he's been probably the leading AGI researcher in Russia, which is a big place and one of the founding nations behind the whole AI field, right? So Alexei, like me and many of us in this room, has been banging his head against this wall for a while. So let's have some of your thoughts on the Hyperon related stuff, Alexei.
Yeah, okay, thanks, Ben. So, in accordance to agenda, the first topic is progress on MeTTA. Sorry, I can hear my echo. So maybe you can mute. AGI room 3. Oh, okay, it's fine now. So Adam and myself are sharing the first topic on progress in meta interpreters, and I will cover mostly the Hyperon experimental interpreter. And since we have quite tight time schedule, it will be mostly highlights, not the full update. Okay, I will start with a brief recap on what MeTTA is. So it was inspired by Atomis, which was a query language in OpenCog Classic. And this Atomis language was initially just a query language, but it had been evolving into a sort of programming language, and that's why we were thinking about the possibility to actually create a sort of cognitive language based on queries to knowledge hypergraph. And OpenCog Classic also contained a unified rule engine by Neil Geisweiler, and this URE was quite cool, and it also resembled a sort of logical language in which you can specify different rules. And the idea of behind MeTTA was to create a more complete language than Atomis, but not as logically oriented, but also functionally oriented language. So MeTTA is somewhere in between Atomis and the unified rule language. So as I said, it's based on pattern matching unification queries, which differs it from Atomis, which queries were not a unification queries, and it is closer to the unified rule language, with which introduced unification on top of queries to knowledge hypergraph or metagraph. So MeTTA is a multi-paradigm language. It was inspired not only by OpenCog Classic components, but also by observing that different languages from different paradigms have some patterns which can be unified. So functional languages have type checking, which can also be considered from the perspective of pattern matching. Logical languages, in particular constraint logic programming, and so on, they also, of course, do the same sort of things. And probabilistic languages also have queries, which structure is suspiciously similar to also a sort of co-querying knowledge graphs with unification, although the mechanics under the hood is quite different, is based on sampling, but it's about inference techniques. And for example, unified rule engine also contained a backward and forward chaining, and forward chaining could be represented as a particular case of sampling. So all these paradigms could be unified within the same, at least syntactic structure, and inference structure can also be sort of parameterized. And we were thinking about a language which could naturally combine all these components, all these paradigms. And of course, we also were very interested in symbolic sub-symbolic integration, because we were working on using OpenCog for semantic vision tasks and so on. And that's why grounded atoms are first-class citizen in MeTTA, in sort of in contrast to OpenCog Classic. And of course, on top of or within this language, different cognitive algorithms should be implemented. So original implementation was and is it's called Hyperon experimental, and we were thinking about renaming it for a few times, but it seems that it's a good name for it, because Hyperon experimental is mainly used for prototyping how different cognitive algorithms can look like in MeTTA, what features are missing in MeTTA or inconvenient for implementing these algorithms. So it's most usually for such things, for fleshing out how the language should look like, instead of providing product level fast and scalable implementations of these algorithms. So it's mostly for prototyping such things, but of course there is some work and ideas how to make it faster. But right now there are various other implementations of both MeTTA itself or knowledge graph storage, which can be either alternative implementations or augmented implementations. And if these are augmented implementations, then Hyperon experimental could be a sort of infrastructure for connecting different components and so on. And among these implementations, there is a distributed atom space, MeTTA-log, MeTTA-morph, MeTTA-optimal reduction kernel, MeTTA-L, and Jetta, and some of them will be covered by Adam, who will be talking after me. So as for Hyperon experimental update regarding what's happened this year, there was a lot of work done by Vitaly Bogdanov and some others. For example, Innocenty Zhdanov and other people who were refocused finally on working on MeTTA from narrow AI tasks, but it's still a very small team working on this. But in spite of it, there was really a lot of work done. Language got fleshed out in terms of core operations, features, and idioms. And improved support for meta computations was introduced, and there were a lot of functions which were put or refined in a standard library, which is automatically loaded within the MeTTA runner, or other libraries which can be optionally imported. And actually, without these libraries, the language here is fun, but it's not that interesting. So these libraries constitute a part of language and practices of its usage for sure. As I said, some performance improvement was performed, and we also are very concerned about usability, because if the language is not convenient to use, to deploy, to build from sources or whatever, then it will not gain traction. So here are some highlights regarding these bullet points. First of all, Hyperon experimented migrated to minimal MeTTA, which was introduced as a sort of generalization of practical development of the language. So there were different requests from the MeTTA users, MeTTA coders, that they want this feature, they want this code to work like this, and so on. And it had been implemented by additional pieces of the interpreter, but then Vitaly Bogdanov rethought all these additional components and came up with a minimal set of instructions which are enough to implement the MeTTA interpreter itself, and it became much more concise and beautiful. And one of the things which we possibly should introduce from the very beginning, but it was introduced in minimal MeTTA, is a unify function. So as I said, MeTTA in general is based on pattern matching queries, and these queries look like this. So you can have some expressions or subgraphs in your metagraph, and you can have some patterns which you want to match against these expressions. And basically it's not a pattern matching query, but it's already unification, because expressions in the knowledge graph can also contain variables, and a sort of unification is performed. But this operation returns empty results if matching or unification is not successful. But unify function allows you to return something else, and it's convenient. So you can have a sort of branching, conditional branching on the level not of if then operators, but on the level of unification itself. And this unification actually applies not only to a retrieval from the atom space, but you can perform unification of just two patterns. And if they unify, then you do one thing. If they don't unify, you do another thing. And it appears to be quite a convenient way to do a lot of operations. Also, minimal MeTTA introduced many, well, not too many because it's minimal, but several very low level, and not that low level, but very useful techniques for meta computations in particular. Eval just evaluates the outmost of expression or function, and stops the further evaluation. So based on it, you can do a very small evaluation steps, although you need to perform a traversal of the expression recursively by yourself if you want to use these functions in complex situations, but for the interpreter, it's precisely if you want to implement the interpreter itself, it's precisely the minimal operation you want to have. There are also other operations to say execute or evaluate some expression in the context of a space. As I said, MeTTA is based on it is built on top of pattern matching, and actually even when we evaluate a functional expression, it is kind of performed through equality queries. So we can we have some equalities in our knowledge graph, and we basically perform unification against these equalities, and you can use just an ordinary match to retrieve the result from another space, but then this result will be evaluated in the context of the top space unless you will manually perform some additional operations on it. But MeTTA operation, it evaluates the whole expression in the context of the given space. There are a few other very particular, very convenient or useful operations in minimal MeTTA, but we don't have time to cover them all. So as for MeTTA computations, as I mentioned, minimal MeTTA operations themselves provide some additional tools for MeTTA computations. A pragma for limiting recursion depth was introduced, which also allows doing some additional analysis on top of what's happening. Reduction termination by atom return type appeared to be very convenient as we envisioned it. Was actually supposed a few years ago, but introduced only this year. So, for example, if you have a function which accepts an argument which is normally reduced, so we have call by value mechanism, then you cannot print the expression itself. You can quote this expression, but then the expression will be printed as quoted. But if we just have an ID function which does nothing but just returns its result as an atom type, then the interpreter will not evaluate this expression further and will print exactly the expression instead of its evaluation result. And of course, it can be done. No val is just a very simple function which can be implemented manually. So it's not a spatial. It's not a special operation, and everyone can use such mechanisms by their own. So this and some other changes make operations over MeTTA expressions within MeTTA itself and the step-by-step evaluation and so on are much more convenient. So regarding standard libraries, there is a lot of things happened, and there is now a seamless passing of items of some basic grounded types between Python and Rust with automatic conversion between them. There are several between modules extended and improved. It's just one random example. Say we have a kind of JSON space, so you can load. You can put some tuples into it as a kind of dictionary, and retrieval is done by MeTTA pattern matching queries. You can also load a JSON file into it and use the same mechanisms. This is just also one more funny example when we represent a argument as a regex pattern, and you can call it with a string, and it will pattern match or does not pattern match against this, and it's not very frequently used, but it shows the flexibility of language, so you can introduce additional concepts into it. But okay, so regarding usability, one useful step was Windows platform support, and one of the problems with OpenCog Classic was that its deployment wasn't supported on various platforms, and Hyperon Experimental had Linux and macOS support from the very beginning, and we finally got a Windows platform support as well. And of course, we pay a lot of attention to Python integration, and it is becoming more and more convenient with some not very frequent but important changes. So there is a very minimalistic, very concise integration of Python functions into MeTTA, as well as MeTTA into Python, although the latter can still be improved, and we have various ideas of what can be done. So regarding performance improvements, highlights in memory atom space with a more compact representation of atoms was introduced. Type checker optimizations were performed, symbol comparison optimization, and streaming code parsing, and other things were implemented. And of course, we are still considering the possibility of much huge optimizations in terms of compilation of some parts of code, and Metamorph, which I mentioned, did this maybe 2 years ago or something like this, via transpiling a compatible meta code to schema and compiling it, but it had and still has different limitations. So Metamorph was recently updated to support the latest Hyperon experimental version, so it's not completely abandoned, and there is some interest in using it. But another project is Jetta, which is a Kotlin-based compiler, and right now it's in the critical phase because before this last year, as I reported, there were different possibilities to compile functional code and non-deterministic code in addition, but symbolic computations were not supported in Jetta, and right now we are quite close to committing and merging a very important part of Jetta, which will work with compilation of symbolic computations, and depending on how this goes, we will understand if this approach is really promising or not that promising. And as I said, both Metamorph and Jetta can be used from Hyperon experimental, so these are examples of augmenting directions and projects, similar like the distributed atom space, which has also recently got a improved adapter to communicate from Hyperon experimental. Okay, I guess it's enough for brief overview. Thank you for your attention.
Thank you very much, Alexei. And next we'll have Adam Benworth come up to talk a little bit more about, more.
So, what's the left of situation?
Go ahead and share on the Zoom.
Oh.
Does that work?
Yeah. But should just present on like.
Yeah. Or you can bring it up here.
Yeah, it should have enough battery for it to continue their presentation. So what's the microphone situation?
It's thinking it up on.
Oh, okay. So I'll just share my full screen.
Are you USB-C?
Yeah, I'm USB-C. Is it 60 watt plus? Else is 156.
It's what I use for my laptop, so I hope it will for you.
Yeah.
Okay.
Thank you. We'll do both USB-C and 241 side. Okay. So let's see. Oh, yeah, accept this. All right, awesome. Yeah, so can you see my screen?
Yes.
I mean, I know you folks can.
Yeah.
All right. And should I use this mic or no? I can just talk and it will be taken up by the ether will transmit.
And also by that microphone.
Yeah. Yeah, that's good. All right, awesome. Yeah, I will be giving a brief overview of the Morg server. So the Morg server is a component of the Morg project that we developed specifically to make it more standalone, scalable. So you can not just use it from the terminal and do one task, but you can do long-lived tasks. This was specifically to address the needs for loading these large data sets where if you are loading something for 8 hours, well, used to be 8 hours, now it's 10 minutes, but if you are loading large things for a long time and you're doing a lot of processing on it, you don't want that volatility of having like a terminal application or a Python script that does that. You want a server which has some guarantees about it, like keeping its state, and then you can interact with that server. Moreover, what you can do is if you have a big machine at your lab, then you can have a server there and a server on your machine, and you can transfer files between and kind of like share progress amongst your research group. Have some reproducibility because you just say, oh yeah, pull the latest like subspace from the server, and then you can work from it, right? So that's the idea. Long-lived multi-computer metagraph processing. All right. So yeah, Alexei already gave like a wonderful overview of the meta language. I won't dive into it that much. One difference between like the way that Morg was kind of envisioned is that the like on the scatter side, you support natively multiple atoms. So you're saying like superpose these things and like add or subtract all these side effects from the space. And we will like just say for the moment, this is a very rough rough idea, but for the moment, like the only specification is like you have some bindings that make the patterns match with the data, and you're putting these bindings on the templates and doing like that step. You consume the rewrite rule and you add it into the space. Now, in the middle of this gather scatter step, we have this processing step where you can do grounded functions. So like your addition and your numerical processing lives there. In between the retrieve, possible even like retrieve from files, future retrieve from multiple machines, do some processing and scatter it back out, right? And then the threat and priority are two what we call system details. So based on which implementation you're working with, these look a bit different. So threats is like in this slide is just your threat number, but it could be like a more structured threat ID if you have like a very complex NUMA architecture or like a very big machine that you're working with. And then priority is also like here just a single number saying when that task should be executed. Like Morg always executes the highest priority task first. But this could also be if you are working in a sampling context or in a theorem proving context, you can have multiple priority queues here and then sample from the multiple queues, right? So that's like the system, like this first pair is like the system parameter. And then we have the gather, process, scatter steps. All right, cool. So like I trimmed it down a bit just to make a like very small point, right? Is that these statements, these processing statements, they live in the space among your data, right? So the processing is actually happening by pulling out an atom from the space, evaluating it, and like doing the updates, the scatter update back into the space in the progress, in the consuming the exec atom. And here I'm just saying like it's the smallest, like the one with the smallest priority, right? And this is actually not a complete formalization, but we'll have to deal with that. Right, so here is like a first fun example. This is a reflective statement. So this one, it's reflective, recursive. So it matches itself from the space in the first non-trivial line. And then can I hide? Like, can you see my cursor? Well, I know you folks can. Can you see in the recording?
Go ahead and leave it around.
Yeah, I don't think so. That's unfortunate. If I exit, probably you can. Yeah, can you see it now? Yeah, all right. Okay, awesome. So here it actually matches itself, right? So it matches itself in the space. It then matches some things it needs. In this step, it needs an instruction counter because we are implementing a counter machine, right? Which is a small Turing complete formalism. Then it gathers some steps, and steps are here subprograms to execute. So it searches the space explicitly for which programs to execute. And then it executes both these programs. So you can see that with the P0 and T0 unifying. And it schedules itself for further processing, but incrementing the clock. Incrementing the clock by 1 in piano. Cool. All right. So yeah, actually, let's show that in context, perhaps. So this is in context, right? Let me increase the font size. This probably doesn't survive display compression, so let's do something like lights, right? All right, cool. So this is our statement, right? And it interacts with the state of the space, which to start out with, that's time step 0. These are our original counter machine registers, right? And then it uses these steps. We have a few different instructions in our machine. In fact, we have 3 different instructions: jump 0, increment, and decrement. And then these act on the program states. So you can see here, right, that we use the program together with the states to execute the full counter machine. So that's all the code there is to it. And yeah, that implements the counter machine. Yay. So let's get back. So now we like for a moment we will just like assume all this, which has been presented before, not in public context, but has been presented before. So like what's next, right? I won't spend too much time on the context as the time frame is limited, but we talked about it before. These LLMs, they are successful, but they are also really, really big, like much bigger than anything that we've tried in this community. And I just want to emphasize the factor here, right? So for example, you can look at the 650-kilometer line of bookshelves, right? I mean, like one of our benchmarks for Mork was, oh, let's put a full book in Mork, right? Noah's like, oh yeah, this is so much more than we can do with Hyperon experimental, putting a full book in. And then you see 650 kilometers of bookshelves and you think, that's a different scale. So how do we get it, right? That's what we want to look at now. So we for like in this case, the strongly connected components task, like we see like a 500,000x uplift from the metagraph processing in Hyperon experimental to Mork. But then we see another like 500x size for what GPT-4 is able to run, like the compute that's able to leverage. And so, like from the left-hand side to the right-hand side, that's you folks, it's the other way around. There is like a number of stars in the galaxy difference, right? So, or something like 12 orders of magnitude. So how do we break that down? And the answer is piece by piece, right? So I broke it down into 4 quarters in log space. So half of it, of the like the first quarter, you get just by as our focus on performance. Compact in-memory representations, we have streaming compression, we have heterogeneous data types, we have log-free parallelism, we have zero copy hyper edge unification, things like this, right? And so just this focus on raw well, performance software and scientific computing engineering, like that gets you already this. Then there is another quarter which like everybody in the room, like we need to do this together, which is the asymptotics. It's mapping the problem into something that we can process fast. It's mapping it into a representation, into a metagraph representation that has all the right connectivity, that doesn't waste too much time like searching through stuff when it could have used something more local. It is leveraging space-wide operations instead of doing this Lisp-style processing in a tight loop. And it is this using the like gather, process, scatter paradigm described earlier, right? So then this quarter is, the next quarter is what I want to focus some of this talk on, which is the multi-node and distributed processing. This covers things like sharding a metagraph into subgraphs, storing metagraphs on disk, which is also very important for like larger scale communication, and then the actual communication between the servers in the cluster. And then, yeah, like the final part is what the rest of the conference is about, right? It's about how do we get to that effectiveness and beyond that effectiveness, but at a less wasteful, in a less wasteful manner. All right, so something I want to cover is that there's kind of like 4 levels to getting from what the user sees and how the user interacts with Mork to the actual in-memory representation. And the first level is the namespacing. So you are familiar from Hyperon experimental that the spaces have this handle. You have a space handle and it contains the space matches, right? And Mork kind of does away with this and it says like, all right, you just have like your structure of your atoms is actually subspacing. So if you zoom into a part of the metagraph, then like you don't have multiple metagraphs. No, you just have one metagraph, and this metagraph is contains different submetagraphs, which are your classical space handles. So if you look at something like this, like puzzle, oh, you cannot see my cursor, like the puzzle atom, it expands into the S expression just below it, where the main arc, this namespace, is kind of inserted into it. Then we convert it to a path representation, which chooses some linearization of the S expression. And this linearization takes into account the indices that you want to use. So for some problems, you will want to use different indices to get fast lookups. And then finally, the internal representation is this alien-looking thing where we have a very heterogeneous data type where we have like the C nodes that you see here, like the C functions or the C combinators. Those are actually multi-thread safe internal representations. Then we have the D nodes, which are high branching factor, like high density representations of the data. And then we have the L nodes, which are the sparser representations of the data. And then we have some more to glue everything together. So what is shown, but like just on the third bits, that is actually compressed down into the in-memory representation that is both compact and allows quick modification, which was a really hard thing to get right. But we are now at like the largest experiment we run was 70 billion like non-trivial atoms or non-programmatic atoms in a single machine. So that would be like about 14, yeah, like I think between about 14 bytes per atom in that experiment.
You know, Christian was showing up on the screen, it's not, but it's right there.
All right, awesome, yeah. So metagraph queries on disk is kind of like the other thing that you need, which is that you have, like I just mentioned, you have this fundamental trade-off between how compact you can store things, how much time you spend on compressing things, finding subpatterns, and how quick you can modify it. And like if we go to disk, then this trade-off is very different. So the initial trade-offs are very much in the we're very much in the camp of we want to support as fast as possible of processing. Well, now we are looking at, all right, can we maintain like 99% of the speeds, but through heterogeneity and through extra complexity expands into even larger experiments where we can have, for example, like a 5 terabytes space, which we can query without having it in memory. All right, and so there is a lot of work that goes into abstracting the algorithms that we have to work over both the in-memory representation and disk representation. And so Igor has been very big help on this part. So towards peer-to-peer communication, what we need is two things. We need streaming expressions where we can process things not just on the scale of here is a whole space at the same time, but we can also like do it more parsimonious. And then the second thing is we want these really compact formats that we can use from disk, and then a shared file system, for example, can address the communication. So I won't go over this because how am I doing on time? Probably not very much, right? So what we can do here, and I won't walk through it fully, but what this example is doing is like slightly compacted pseudocodes, like the original Python code was like 40% larger, and more lambdas and ugly terms. But what this is doing is it is distributing a task. It's distributing a space over multiple machines. And then on each of those machines, distributing that over multiple cores, and then aggregating over the machine, over all the cores of the machine, and then aggregating over all the machines in the task. So this is like a two-level MapReduce, right? And this is, yeah, in like I said, originally like 35 lines of Python code. And this is running today, right? This is not some hypothetical, like we should be able to do this. No, like we can do this processing now. And it requires some management of prefixes. So it requires, like in the partitioning that I said here, right? Like it requires some care about like how you're structuring your subspaces that you can actually parallelize them. You see the work adds operator in a couple of places here. So instance work adds. And this manages namespaces. You see arc datasets.namespace. And then just as you do, like if you're familiar with deep learning, you have like these like micro batches and macro batches, you're doing the same thing here, right? Where you are processing like the macro batches on the cores, and then each task gets a micro batch. And so you have to do some orchestration. But what we are left with is almost a linear speedup in this case. So like a very high efficiency, about 86% efficiency for the cores that we are leveraging over multiple machines. Now, of course, I will be the first to say that not every task parallelizes nicely, and that communication speeds between nodes of a cluster is very, very important. But for the cases you can get away with this is really nice, right? I have like two big machines at home, and I regularly now use these for experiments where they're like just on a casual Ethernet connection over like a switch like that they have to communicate, like a off-the-shelf switch, and they're able to do some like pretty nice reduction communication steps where like they can cooperate in like a tree to reduce, for example. I've also experimented with some message passing. Of course, then the latency really starts to show up when you're doing message passing between the two machines. But like with some careful management, and like this example is carefully managing this, we see great efficiency. All right, so if you want to like have the tutorial version of this, like how to do this at home, like without a multi-processing, just a multi-machine, then it's very simple. So I had it on slide, but I will take a risk and just do it live. Live multi-machine orchestration. Let's go. I have no idea how this is going to work out, but so first of all, what we want to do is we want to, and I'm actually going to run them on my laptop, because if I need to SSH into other machines, this is going to be a mess. So we're going to specify one port for one server and just a small number of threads because it's a small laptop. And so we can use these commands in the Mork repository that we can all find. And then we see listening on this with four worker threads. All right. We will start another one of those, but with a different port. So this is listening in 8002. And then what we can do here for example, Python, we can name one Alice and the other one Bob and connect with them with the context manager. So the with statement here. And then what we are going to do, just to start with, right, is for each participant in Alice Bob, we are going to go into some namespace. We are going to upload some number of atoms. And this is like actual sequential or blocking, right? It actually does the upload. And then we do this non-blocking transform. And this is taking like an outer product. So it's like kind of the slowest operation that you can do on this. And then we are gonna block on all the tasks. So we are distributing to two servers, doing an outer product on both of them, and waiting until both finish. And so let's run this. So let's do Python. All right. And what am I doing wrong? Yeah. Okay. Maybe nothing. So right. So this is was uploading this to this machine, and we should be able to check both, right? That it's actually it completed the transform commands, and it's actually works. Yay. So multi-machine distribution. Of course, like if we had more time, then we could do something like this, for example, which I won't try and run it at the moment, but we can basically say, right, we are doing this not just on multiple machines, but also multi-core, where we need to chunk up things a bit more. And then in this way, we add something like not just the pairs, but the pairs per core. And we don't just match on the integers, but we match on the integers here on a specific core, right? So this would be something like this, where we have a static namespace, and then we have a dynamic namespace in here. And this, or something like within added distance 5 of this, should actually distribute it over the cores also. So then instead of just distributing it now over 2 cores, we distribute it over however many cores the 2 machines that other have. So yeah, that's really fun. You can do communication with paths import and exports. I've shown this like on a internal presentation. And yeah, you can try that over here. You can just like build a server in the server directory, and run the Python codes that I've shown you. And then I have a closing note, which is like relation to MeTTA. This has been like often asked question, which is how do these two relate to each other? Ben already gave like a slight hint of it, which is that MeTTA handles this decentralized compute, right? I've shown you servers running on multiple machines, but there was no consensus protocol over this whatsoever. In fact, there was even not any fault tolerance over this. This is like just raw scientific compute. Like you own a box of machines here, you expect a failure rate of 70% if you're working in biology. Like this is very reasonable, and you run it over the rack of machines, and lo and behold, sometimes it works and it's really fast. So that's kind of the role that the Morg servers plays, and I'm okay with that. So it alleviates the bottlenecks found in the existing implementations, like on the single machine scale, but also it scales much further, both to multiprocessing, right? I ran it on a machine the other day. No, I cannot talk about it. Anyways, I ran it on a machine with a lot of cores, right? And it scaled up to many hundreds of cores, let's say. And that was really exciting. And if we have many of these machines, then maybe you can scale to many thousands of cores. That would be really cool. There are very few graph databases that actually hold this up. And the key to that is the subspacing that we talked about, is the prefix indexing that we talked about. All right. So what this does not provide, the Morg server does not provide like a comprehensive to replace MeTTA as a language, right? So it does provide minimal MeTTA 2 on top, and it provides like the client API and the APIs for communicating with it. And it provides a RISC library, but it doesn't provide like a full programming language stack. MeTTA does. So MeTTA wants to put Hyperon on solid footing and just formalize the way that we are tackling these problems, right? Like if you have AIs exploring the world and they want to model a computational phenomena or model a phenomena computationally, then they can have this DSL that they are programming in, and that gets compiled into an interpreter, which can be run up. It's really cool. It's not what we are doing. In theory, like MeTTA has a higher like performance ceiling, right? Because you actually have the full compilation step, and you have a lot more knowledge about what's allowed and what is not allowed in the space. So like the reductions, it's much less chaotic. You can optimize it further, but of course, like there is complexity to get it, right? The MeTTA cycle's first focus is the decentralized compute and the fault tolerance, like while here the just plain performance is what we went for, and pushing the envelope on the size of experiments we can run. Right, that will be it for me.
Thank you.
Do we have questions now, or?
Probably a good time to approach.
Probably a good time.
This is the end of the implementation. You know, like I was supposed to.
Any questions from the room? Yes, from the back.
If you have, there's kind of two things that I'm wondering about. Great presentation.
Thanks.
If you're looking at, if you have, say, for instance, two different groups, say, for example, that start from an existing node graph, and then they work independently inside of it. And then you have, different versions of the dots. Okay. But say, for instance, you also can do your just multiple users and have to pass out. And I wasn't very clear into the ladder. It's not the first, it's the ladder. What's the policy behind,
Yeah, so yeah, I will briefly summarize it. Like, so there are two questions here, which is one, like, if you have multiple users together and they want to like merge data and merge their progress together, like what guarantees or what can we provide there? And then there is the question of like, if you have multiple users which each their own task, like what are the guarantees of like non-conflict and transactional semantics that we provide there? And so yeah, that's a great question because I forgot to put it in the slides very explicitly. So the merge back step is based on the same principle as all the other concurrency is based on, which is the exclusive rights on a prefix. So if you have a subspace, then only one person can write to that subspace at a given time, and the rest will be rejected to write to that. And that is like a synchronization boundary, like on a single machine. You do not impose this synchronization boundary over like many machines because we do not guarantee like multi-machine consistency. And then on the individual users side, we have this idea of event logging, where we when a operation starts or is submitted, and it is finished, we keep track of that, and we are able to rebuild the database up to a consistent state for the known requests. And this does require like rebuilding some of the timings that we had originally, or not the specific timings, but like the semantic dependencies that we got from the timings. So yeah, does that answer your question? Okay, well, what's the part that you're still interested in?
well, I guess the say, I guess the base of the person explained the prediction things, merging the version. Yeah. So, I mean, basically, it's like back and not turn that way and program. You know, actually, idea for the knowledge of clarity. So, you know, having different versions of and so, obviously,
Yeah. Yes. Okay, so like going in on the source control specifically, we do not provide like a paradigm, or like we do not impose a paradigm for doing that. So except like we are like, all right, if you're not writing at the same time, then like it's good. It's a good policy for us. Of course, it may not be a good policy for the lab or for the experiments. So in if you want to scale this out, like we don't want to impose like a specific way of handling this, but like you could perfectly have a Git level version control over these spaces. You can put this on top, and that's quote unquote just works. In fact, like a colleague has demonstrated this exact experiment where they implemented like a diffs mechanism and they implemented like a hash consistency. So like that is possible, and in fact desirable for large scale or some large scale experiments. But also I feel like there's no universally good solution to this. As I've talked to folks, for example, in the biology, they have data, like many terabyte data sets, and they cannot use Git, right? They're like, this is way too slow, and it doesn't match up with the way that we work in the lab. So they have a different version control environment. So I feel like we should, I would like to accommodate these, but not necessarily impose them on a server. Oh, sorry, Scott.
I'm not sure if the idea it's 80% file. Yeah.
No, not really.
Well, I mean, what I'm, in terms of like the granularity, it's not going to be benefits. I'm not sure whether.
Oh yeah, the ideas of Git, yeah, like indeed in some concurrent contexts, like that the Git doesn't make sense, right? So yeah, correct. Yeah.
And you know, a lot of, so in terms of like so for instance, this goes out. So I wasn't quite clear in terms of what you're saying. If you have a point, you're saying on the start of the right.
Well, like, yeah, because yes, so we reserve the ability to reject operations, right? And we will tell them up front. So there's at no points will somebody come back to the operation and go like, oh, this operation failed. No, if an operation fails, we tell them up front, and everything else is infallible. And so if you do an operation like, oh, I want to insert this, and somebody else was writing to that, you will get back a like, hey, we didn't accept your transaction because somebody else was writing. Yeah, well, in a way, because you have the granularity, so you can zoom into smaller bits and then still find a way to write to it. But yeah, like on that scale, yes. Yes, sure thing. Yeah, I have a couple of slides on that, like this one or. Oh yeah, this one is not. It's not a very formal rule, but yeah. 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 So this happens like atomically, quote unquote. Yeah. So so these things don't fail. So yeah, but that's a very good clarification, Greg, is that indeed the gather, process, scatter step, that's like a single unit of like processing in the database. Yeah.
Right, I wonder, did you give a few sentences of update on the MeTTA to MeTTA IO to morph and build that, which I didn't do for the. Oh, sure. I think it.
But you need to much questioning.
Or just, yeah.
Just put him on the spot, right? Like,
Well, you know, Jeff, I know. No.
I mean, normally you're waking up like an hour ago.
Yeah, that's right. You're that teleporter working? Not yet.
Thank you.
Wait, is there a mic or should I just?
Oh, no, just it's up here.
You have to stand here.
Here-ish.
This is.
Right. So, how many people actually know the context here? I know Nil knows, and I know Ben knows, and Charlie knows, but so let me just give a little bit of the context to set the stage. We engaged with the MeTTA community to also provide a throughput scaling mechanism. So as you add more processors, you get more total throughput. And that was based upon the row-based architecture. So I can't go too deep into that, but basically the row calculus is a best of breed model of concurrent computation. So the gather scatter model that Adam was showing is in that same family of models of computation where you have processes interacting, and you can think of these interacting processes as basically like the notion of an atom space. It's a little bit more articulated. But anyway, so the row model scales so that you can eat as many physical threads as you have available and turn that into throughput. It maps nicely to the meta notion of space, right? So roughly speaking, there are no.
I wants to give you a marker, but it's a permanent marker, so.
Oh, right. There are no markers.
It'll be a gift for that too.
But anyway, so while we're waiting without elaborating that model of computation very much, the other thing that one of Ben's visions was that you could impose different kinds of type systems on MeTTA to get different kinds of behavior. And so we were working in a very similar area, but our idea was that you could, from a given description of a model of computation, and I can talk to you about what that is, what a model of computation is, but from a description, you can auto-generate what's called a spatial behavioral type system, which has extremely powerful properties. It allows you to state at the logical level. I'll take all of them. What that does is it allows you to be able to state, for example, safety properties, liveness properties, and security properties. Right. So we have a family of algorithms called OSLF. Hey, Kelly. Which you input a model of computation, and what it outputs is a spatial behavioral type system. And that that has the that sort of fulfills Ben's vision in a certain sense. So MeTTA gives you the smallest Turing complete self-descriptive or self-describing language in which you can write down these models of computation. So we encode them as what are called graph structured lambda theories. And then it can synthesize the spatial behavioral type system. And that's just the declarative side. The other side is the execution side, which is effectively a version of the row model that has this kind of gather scatter mean sort of core execution, and that gives you the notion of space where processes can come together. This does not sound very coherent, so let me make it a lot more coherent. So let's start with I'm going to start with a teeny tiny model, and then
We'll have to write it large, but.
yeah, I'll write it. I'm just gonna describe a toy model and then show you how it expands in a step-by-step fashion, and then talk about that'll give you enough context to understand the updates, right? So this model, not that one. There we go. This model is expressed in terms of processes, P and Q. And processes have several different options for what they can be. They can be the empty process, which does nothing. Or it can be a process which is waiting for something that matches a pattern from a space. And then it becomes a process. Or it could be something that sends to a space an atom. But atoms are just processes. Or they can be two processes that run concurrently. And now here's the one tricky bit. Which is that it turns out that all spaces are just the codes of processes. And since the space is the code of a process, we can we can take the code and start running it. Right, so this says run it. And then dual to that, we say that a space is the code of a process. So that is a toy model, teeny tiny, but this has this nice property that if you that it scales, so it eats as many physical threads as you have available to you and turns that into throughput. So this piece, if you so let me describe how programs like this execute. So if I have something that's waiting. So it's waiting for some data in the space that matches the pattern. Running together with something that is putting an atom in the space. Well, that program evolves to the program P, in which the code for Q replaces, provides this. Let me, just to make things simple, I'll just make it a simple variable. Right, so the code for Q replaces the variable. More generally, when this is a pattern, we generate a bunch of substitutions depending on how that pattern match happens. But this is just a single variable substitute. Right, so this is how code evolves. Right, and so the idea is that these are logical threads. And they only synchronize when there's a match like this. So if there's no conflicts, so for example, if I have something that looks like this, say for E1 from S1, I'm gonna stop writing space. E1 together with on S1 P1 together with or P2 from S2 P2 together with S2 Q2, right? This runs completely independent of that. So these will be mapped onto two completely different synchronization events, which then go to two completely different physical processors. Right, so more processors equals more throughput. Right, now to this model, we can extend in two different directions. One direction that's really crucial is being able to write down things like I just wrote down, right? So this spec is a spec for a model of computation. It is itself a graph-structured lambda theory. So the first part of the graph-structured lambda theory is the set of shapes. All right, so these are the shapes, and then that rule that I wrote over there is the behavior. Right, so it's a set of rewrites, and in between, we need one other piece of data, which is sometimes your syntax is too fine-grained. You need to coarsen it. So let me give you an example of what I mean by coarsening the syntax. So this thing here, the parallel composition is a commutative modeling, right? So in particular, if I have a process which is running together with the process that does nothing, that really ought to be the same as just the process, right? And if I run the process if I run P in parallel with Q, that's really the same as running Q in parallel with P. Right, so I need to be able to add equations like this to a model like this. Right? So being able to write down some shapes, some equations, and some rewrite rules. And those rewrite rules have to have some nice properties. For example, I can say in which context rewrite rules occur. Right? So, for example, I want to be able to say, well, suppose that P reduces to P prime. Then I get to conclude that P in parallel with Q reduces to P prime in parallel with Q. Right? So this is saying the context in which I can run this rewrite rule. Right? That's very important because, for example, in the original Hyperon experimental, they didn't have these kind of contextual guards. And as a result, you'd have to go searching the entire syntax tree for a redx. Whereas, this particular model, all the redx's are at the front of the top of the expression, which is why it's very interesting as a computational model. There's no redx's that can run deep inside the expressions. Right? So that's very, very important if you're trying to get performance. So I want to be able to write down lots of models, all the models of computation. So I want to be able to write down a theory of computation that has shapes, equations, and rewrites. Yes.
Am I correct in remembering that a red X is over top two?
Yes. Yeah, it's an expression that could be reduced according to a rewrite rule. Okay, so what MeTTA does is it expands this model of computation. Now I'm working on two levels here, right? So I introduced you to a model of computation, but then I said, hey, if we take a step back, this is a way of talking about models of computation. Right? So I want to be able to write down, I want to expand this model of computation with the ability to write down models of computation. And MeTTA is the language in which to do that. It allows you to write down what are graph structured lambda theories. So one way to think about it is if MORC is the database, MeTTA is the schema language. And if you have a graph structured lambda theory, like this one, the one we just have on the board. So if we have a GSLT, so like the one on the board, right? Then I can feed it into this family of algorithms, which we call OSLF, or operational semantics and logical form. And out pops a spatial behavioral type system. And part of the importance of getting this right is that if we do this well, then there's a beautiful theorem that holds for all of the spatial behavioral type systems that we generate using these algorithms. In particular, we have that P is bisimilar to Q, so these are the same program effectively, if and only if for every property, say phi, in this spatial behavioral type system, P satisfies phi just when Q satisfies phi. That's the property we're trying to preserve. Now, this is not just nice in terms of software engineering and making sure our programs are correct. This has implications for AI that we don't have time to get into that. That has very strong implications for AI. Okay, but so the OSLF algorithms guarantee this property. And as a result, whenever I have P satisfying some collection of fees, right? And I have Q satisfying that same collection of fees, I can substitute Q for P. that the list cost substitutability property is now encoded formally in a way that we can check with compilers. So that's another piece of the puzzle. So let's take stock then of what we're talking about.
And very, you said, if more is the database, that I is the.
Schema language. Yep. Okay, so the ability to write down the models of computation, that's the schema part. And this specific model of computation is how you execute them. And we can encode meta to that model of computation, and then we can make this model of computation perform very well by encoding it into more. So that's the trick. And now, so that's enough context now. So you had a question.
When we use the word spatial, we mean like methodological or even like. I'm not sure the meaning of spatial.
Good, very good question. What it means, the spatial, the logics that these algorithms generate, they bucket the formulae into 3 different buckets. There's a bucket for collections, right? So and or and implies and negation, these are all about collections. Right? And then there's another bucket, which is about structure. Right? So if I take a program term, a legal program term, and I knock a hole in it somewhere, like let's say here or here or here, right? Then I could replace that hole with a formula that says fill the hole with only things that match this formula. So that's the structure bucket is what we call spatial types, right? And then finally, there's another bucket, which is the modal types. And that's the behavioral stuff, right? And what's super cool is that the way we achieve this property is that the modal types, they use Hennessy and Milner's interpretation of Kripke's notion of possible world semantics, but we've updated the notion of observation. So when we write the possibility operator, what we put inside here is a context, right? So when I write a formula like this, so we say that P satisfies this formula, means that when we put P in the context K, then it evolves in a single step to a P prime that satisfies P. That's the meaning of this statement, right? So these are the 3 different buckets that are auto-generated by the OSLF algorithms. These things, they are completely determined. The notion of observation is completely determined. That's very important. Again, it has implications for AI. But right, so now I can answer Ben's question. Sorry for the long-winded.
That's right. We didn't need to eat lunch today. AGI is more important.
I'm so sorry. I apologize.
But it's very interesting in the.
So there are 2 things in the pipeline, right? We want to look at the updates on MeTTA to MeTTA-IL. And we want to look at MeTTA-IL to more, sorry. Okay, so there's a bunch of boilerplate stuff that we're down in the weeds on right now. So in particular, when we defined MeTTA-IL, we didn't bother with all the primitives because we knew how to do those. But now when we're doing this compilation, we have to put all those in, right? So we've got the arithmetic stuff in, and the string ops are done, and we're just writing a bunch of tests to get that done. Once that's done, then Adam has a really nice bottom-up algorithm. So I should mention that Mork is actually a sub-language of MeTTA. So all the Mork operations are available directly in MeTTA, right? And Adam has a nice bottom-up algorithm for interpreting meta and on top of PathMap that we will simply pull back through this, right? And so we have this sketched out, and we'll be starting to cut that code after we're a little bit farther along with this. But that's essentially where we are. Does that make sense?
Yeah, so the whole pipeline is done tomorrow.
Yeah. Yeah. Tomorrow somewhere on Earth. Yeah, but that's basically the update. And I encourage people, all of our code is open source, follow the code. Please go check it out. I think you will be surprised by how compact it is to write down very, very sophisticated models of computation.
And the 10th grade meeting.
So just to give you a sense of how powerful. Okay,
I apologize.
no, that's totally fine.
But if you can provide some links or some information, we'll provide that to attendees and to the people online who couldn't see the drawings as well.
Absolutely, yeah.
Fantastic.
Yeah.
So, thank you, Greg. Thank you, Adam. Any questions, point also something about Jota?
Not right now, no,
Okay.
because we need to shift gears to AI from infrastructure, you know, I think we probably can take a literally like 2 or 3 minute bio break now, and then we can resume and we'll talk about probabilistic reasoning and evolutionary program learning and motivation and attention. We pushed the entire AGI part of this to 15 minutes. Not really, we're not gonna try to do it that fast, but what we've talked about so far is kind of the high end plumbing underlying Hyperon, and the whole point is the AI can implement on top of it, which will be the next part. I think so.
Lunch is at 1:40. So
We've got an hour and 15 minutes to cover all the components of our solution. And I think who's next, you know, is that it?
No, bathrooms, restrooms, and coffee are right outside the door right now.
You know, and
Power guy.
Oh.
This is.
What do you want?
And
Oh, right, so you just want the, yeah, right, lunch.
Yeah. Oh.
Yeah, that's our UK flag.
I think there's all interest of time with that. Something on that.
When I left my sorry.
Yeah. I can.
Who needs lunch? Yeah. Operational tonight.
So do I need a mic or something?
Nope.
This is picking up.
All right, so now we're going to fairly rapidly go through the actual purpose of all this, which is the learning and reasoning algorithms that we're enabling using all this infrastructure, and then some of the applications that we're using in order to both do useful things in the world and flesh out and tune the infrastructure. So I think Neil will say a few words on pattern mining. Then, while Neil has been the main guy behind PLN, the PLN development group has been expanding. So we'll have some colleagues talk a bit about PLN progress. Then I will talk a bit about both Moses program evolution and motivation. And then we'll go on and talk about some of the applications that we're using to explore and leverage all this. And this is really a sampling of the different AGI-oriented algorithms that we're building using all this framework. We're not going to be able to go over everything, but it should give these are both important parts of our cognitive architecture and are good examples of how to use this infrastructure to do AGI-ish stuff. I'd say when I talk about motivation, which will probably be I guess it doesn't matter what order I go in, but when I talk about motivation, that will give more of a view of the overall cognitive architecture within which these algorithms are doing things. But for now, let's go sort of cognitive algorithm by cognitive algorithm one by one and see how they can leverage this cool infrastructure.
Okay, so yeah, for the interest of time, I'm going to try to be as quick as possible. So
You done?
What?
You done?
Yeah, well, no. I wanted to go negative, but okay, don't do that. Yeah, so this is not my work that I'm gonna present. This is the work of Tewandros Nibret and his team in ICOG. But so the work they've been doing is to port some work that I had previously done on OpenCard Classic about pattern mining. I've been very interested over the past years with the idea of reframing learning into reasoning. So that's one example. So pattern mining is, well, you have a bunch of data and you try to find frequent patterns. The interesting part is that you can reframe that as a form of reasoning somewhat. I'm not going to explain in detail how, but basically this is the work that this team has been doing to port that to Hyperon, our new framework. And man, I can give you 2 sentences about pattern mining. You have a bunch of data in a graph. You start from, say, a very abstract pattern. It's going to match everything. So you have a very high frequency of that pattern. Then you can specialize the pattern. The more you specialize, the least frequent the pattern is going to match the data. But if the pattern remains sufficiently frequent and specialized, then you carry a lot of information. And that's very useful it has a lot of predictive power. And the advantage of reframing that as a form of reasoning is that you can go from purely abstract pattern matching to then start to introduce semantics, some reasoning that you need to introduce in order to reveal more patterns at the surface. And so, okay, I said I would be quick. So I think I'm done for now. And now I'm going to leave the stage to Patrick.
Actually, since he was
Yep.
so quick, I would add a sentence on pattern mining and more related to some recent discussions we've had. So we had in OpenCard Classic a nice greedy pattern mining algorithm, which basically looks for frequent or surprising patterns across knowledge graph and knowledge meta graph. And this is nice, and the team in Ethiopia working with Nil have been porting that to Hyperon and using all this funky concurrent processing infrastructure. We can do this on multiple threads and multiple parts of the same hypergraph without any contention and synchronization issues, which lets you scale up pattern mining. Given the nice distributed processing infrastructure we discussed, you can take a big atom space, put it among many machines, and divide it into pieces, and then you sort of mining patterns among the pieces on different machines, efficiently using concurrent processing on different machines. And because it's a very simple algorithm relative to many other things we're doing, it's sort of good test bed for all the processing infrastructure. The other thing I've been thinking about and talking about with Adam and others a bit is, if the data that you have is naturally like a DAG or a forest of DAGs or something, rather than a general tangled up graph. For example, a collection of programs stored in atom space, which will tend to have a natural DAG structure. If that's your data, then you can implement pattern mining in a more efficient way, closer to the morph metal, basically. So if you're pattern mining like in a social network graph or something, with just a big tangled up graph, then the kind of implementation Neil has been alluding to is what you want to do. You have a sort of concurrent processing friendly 3D pattern mining algorithm. It tries to learn little patterns, find the best ones, try to grow them into bigger patterns, find the best ones, try to go into bigger patterns, find the best ones. And that's what you do. And then these efficient pipelines we've been discussing make that pretty fast by going from meta to meta IL to more. Now, if you have a collection of programs and DAGs or something, you could then implement pattern mining in a more efficient way as basically DAG pattern mining on more, and then you're removing some interaction. You're going from meta through to more. And this, I mean, here this is highly technical gathering, so we're discussing all the plumbing, right? Now, from the end user standpoint, what you would like is have a pattern mining problem. If it's DAG-ish, then you just like revert to the super efficient implementation on more. If it's more cross-connected network-ish, then you use a more generic pattern mining implementation, which can still be fast, but not as fast. But at the nitty-gritty level we're talking about here, there's a whole different approach to implementation you can take if you have pattern mining among DAGs, and you can implement that in Adam's minimal meta too, very close to the monk level, right? And that's
Yeah. The beautiful thing about Mark is that in a way, the compressed representation is already a form of pattern mining. So if you can take advantage of that, then you can really keep things up. What we talked about on the I believe weekend call was that some subpatterns can be shared among many places in the morph space. And there's not only space memory, but there's also, as we mentioned, like a form of compression in itself or a form of pattern mining in itself. And in fact, I believe Peter and Remy have been working on using some kind of const hashing or hashing of subspaces to find subpatterns in the space and compress it in memory. So if you have a very long-lived process on a morph server, and there is not a lot of work going on in this particular subspace, you can spend extra compute, right? If you have a machine with some cores that are not doing anything, you can spend those cores to do pattern mining on the morph space and compress the space further, like as an optimization. Yep. That's a beautiful synergy.
all right. So now Neil wanted to be very compact, but we can move on to PR now.
Yep.
Thank you very much, Neil. And Ben.
Right. I will start with the first part, introducing the PLN. So basically, after the Dubai meetings, we have been working on we started work with PLN, and we just yesterday committed and released the PLN 0.5, just put a tag on the release, and then everyone would just come and check it out.
0.6.
A couple of months, Right, 1 second. So what are the fuel and motivation of the PLN is, first of all, we wanted to create reasoning finally, which is operates on the probabilistic logical networks. And the reasoner has to be practical and able to reason on the non-trivial tasks, which is important, and has to do it in real time, in a data efficient way, and sorry for that, in explainable way as well. So we want to implement that in MeTTA language. That is one of our requirements to promote the well-structured, maintainable package, which has and features the clean code base. And we want to utilize this across multiple domains, across the domains that require real-time learning. Why does it do that? Sorry. Yeah, after, I think I checked that already. So we want to utilize on multiple domains that require real-time learning and as well as uncertainty estimation, like robotics, for example, or like some probability predictions, and some reasoner that could have seamlessly integrated within AI stack with other state-of-the-art deep learning tools. And we want also to be able to integrate seamlessly with some MeTTA applications, like, for example, library MeTTA and with full-featured AI architecture. So that said, here you can see basically we start with a little structure, very abstract overview. So the structure we devise is a module by design. It has a real practical approach. It's easy to support and integrate, and it's very distinctive. So having this modularity in our minds, we start building the MeTTA files. Isn't that? Maybe I just have to.
I think you have to apply to all. You're doing it slide by slide. If you uncheck after and do uncheck after.
I get it.
Do apply to all. That should work.
Okay. Every time something new. All right. So having this modularity inside, we've been creating the package by package and correspondingly naming them. So we have so far 4 packages, each of them with basically a MeTTA files, deriver, rules, formulas, and utils. The deriver is for the inference control. So far, we only have a declarative inference. Later on, we're going to expand it in multiple files, like temporal, procedural, whatever is required. Rules only calls the inference rules, like abduction, deduction, and definitions of the rule. Formulas holds the truth functions, and utils just has the functions or methods common to all of the packages. Now, we're still waiting for the practical MeTTA, and while we're waiting, we created PLN reasoner, which is runnable by our own metamorph. This metamorph is a method to scheme translation. It uses the scheme macros. Basically, for each MeTTA construct, it has a dedicated corresponding macros, and it covers a considerable subset of MeTTA functionality. So anyone can really use this to create practical applications. So we're using this to accelerate it, to precompile it basically from MeTTA to skip to C and then just run the binary. Why? Because we need, for example, later we have the use cases to run on the robot and we require real-time performance on that, which we could not get by MeTTA or Hyperon experimental. What does PLN 0.5 so far include? So it includes those set of inference rules. So we start with deduction, induction, abduction. We have the revision, we have the bond exponents, negation, like whatever, equivalence, implication inversion, invariance inversion, all set of rules. So we're going through the PLN book as well as all the repository and work in progress repository, which is the scheme code, to really refactor, to re-understand and re-implement completely in MeTTA. Each of those rules has truth functions, corresponding truth functions, which computes the truth value, simple truth value, basically the strength and the confidence, right? And the inference control, so far we do have the declarative control only as of now, because this is the very first step. We're just working a couple of months on this. So yet still it's very simple and yet effective. It's cycle-based. Now we just recently, probably last week, before we just had a derivation tree, now we kind of implemented the priority queues away, and it still has, it stops whenever we supply the depth of the inference.
this is how, again, we're going a bit faster than needed, but this is how we implement the inference rules, including the truth functions. So again, we're going through multiple sources and we're implementing them. This is the deduction, for example, you see over there. Over here, this is the inference rule for the deduction, and over here, this is the corresponding truth functions. The problem is that not all the strength and confidence of the truth functions are really straightforward and not even before been well thought. So it's still kind of a research topic. For example, what has to be the confidence in this particular case? Is it minimum will suffice for the confidence or not? Once we expanding the use cases, we're going to monitor the performance of them and correct correspondingly. So as you can see, very informative, very easy to follow, very easy to read. So this is for the induction, corresponding truth induction, or the abduction, corresponding truth abduction, and importantly, revision here as well. And they have those borrowed from NARS. We have confidence to evidence and evidence to confidence transformation functions, which will be like a supportive functions we only use as a truth functions. I think I'll go right to the inference control as of now. So we have a declarative inference control. That means it's a type of semantic inference that require a common term to be shared between the premises. And it operates using two queues, beliefs and tasks. At start, we start with them the same, but once the inference proceeds, the tasks is kind of like serves as the short-term memory or the priority, attentional focus, so to say, of the system, and the belief serves as a long-term memory of the system. So we have those corresponding sizes there. So the task queue currently has 20 elements. The beliefs has way bigger, 10 times bigger, 200 elements. And the maximum reasoning depth we now can do up to reasonable 20 steps. So we can repeat the operation 20 steps, and we call it the cycle. So this declarative cycle basically begins, we take one task from tasks queue, right? And we basically remove it from the task queue. Then we do the inference with every belief in the beliefs queue, right? We produce some derivations, like here, basically, right? Then what we do, we basically union derivations and tasks together, and we remove duplicates. By removing duplicates, we have to look for the term. It has to exact term. It has to have exact truth value. And very importantly, it has to have evidential base. Evidential base is the trace. Whenever we try to derive, we keep track of the elements the derivation is produced from. So very important concept. After that, we do the same with the beliefs. We union beliefs and derivations and remove duplicates. And then we limit the size of each of them. So initially, the size is bigger, but after the second step, it's already become task queue becomes 20 elements, and the belief queue becomes 200 elements. And then we continue to do the same, removing another task and doing the same for 20 steps. Max reasoning depth is 20 steps. Important to say that those priority operate as of now on the idea of confidence. We still, again, research in progress what to really use until we come up with some attention and resource allocation control, which Matt will introduce. But as of now, both of them are being operated on the idea of the highest, basically removing the highest confidence belief or highest confidence task. I think we can go into the use cases. So we have three use cases, which is attack smokes. We have another, that use case just covers the basic functionality and how the system is able to perform. Then we have the toothbrush example, which shows it's a bit more complex derivation. It shows the system is able to learn the generalizations and properties. And then we have the real-time application in robotics, which is an extension of the previous work we showed in Dubai. And now we have connected it with the ARM actuator actually to manipulate the environment, which is very important. The robot now can actually walk, not just without just walking through, but explore and manipulate the environment. Patrick, you want to see the demo very fast? You can use that.
Go with the slides.
Yeah. If you need, you can remove the low battery, right? And shoot the demo here if you want.
Oh, thank you. Okay, check. Oops. Okay. Perfect. Thank you. So in terms of use cases, there previously in the previous slide we saw this default parameters like for the task queue size and belief queue size and maximum reasoning steps that are taken. And the idea is here essentially that you, as the user of PLN, you can say how many resources you want to allocate to the reasoning process. Imagine you have a bigger knowledge base and you want to ask a question to the system. And then for that question, there might be multiple reasoning paths, there might be multiple contributing factors that make a certain response more likely or a certain answer more likely. Imagine you want to determine whether a certain person in the knowledge base is a smoker or not. And then you might have other knowledge pieces in the knowledge base. For instance, you know the person has bought cigarettes, or maybe you know the person is befriended with smokers. And so you have multiple pieces of information that might increase the likelihood that that person might smoke. And you want to take this into account, but it's different pieces of information that need to be taken into account. And taking each item into account takes computational resource. So this is where we have this task queue, belief queue sizes, as well as the amount of inference steps we allow the PLN implementation to take for a particular reasoning problem. So, and this will be relevant now also in the experiments. So the one with the smoker is a famous reasoning example for Markov logic networks called Duffy smokes. So essentially, it's similarly as I mentioned, you have given knowledge about different people and who is befriended with who and who smokes. And then you try to estimate like what's the chance that a certain person smokes. And you might also have some additional knowledge about smoking leading to cancer. So you can also ask yourself the question, how likely is that person to develop lung cancer, for instance? So this reasoning example shows a quite natural use case for PLN because it's, how to say, it can easily be extended. The knowledge base can easily be extended, and you can essentially show this probabilistic reasoning ability, which does not only give you a true or false assessment about whether someone is a smoker or not, but really gives you a probabilistic assessment. The more data that supports that a certain person smokes or gets cancer, the more can the reasoning reveal that probability. And here you see how this is encoded. It's quite natural encoding, which we chose initially for this initial release. We used the encoding that is very close to what has been in OpenCog Classic. So we have been trying to replicate the reasoning functionality that has been in OpenCog Classic. But I think in the meanwhile, it's also a bit beyond that, also because this reasoning queue mechanism is turned out to be very effective already. And also since we managed to accelerate this reasoning using our MetamORph compiler, so we wrote the PLN implementation in metacode in a certain subset of meta that can both run with Hyperon experimental and also run with the compiler, essentially. Yes, so this was about Duffy smokes, and the next example is, as Peter mentioned, is more about decision making. Imagine you have different involved objects and you know different properties and you want to do something with this object. Could be simply as there's a screw somewhere in the wood and I want to unscrew it. How can I do that? Ideally, there would be a screwdriver I could use. What if there is no screwdriver? Maybe I can do something else. Maybe there's some object that is made of plastic. Maybe I can melt that object. Maybe I can reshape it in a way so that then I can then unscrew this screw. So